Let's look at one more example to get some additional practice using that Mason's rule formula. So in this case, let's find the transfer function for a system that we had analyzed previously as a block diagram. So this is on page 4.7 in the notes that are posted on Canvas. So the first step, of course, would be to convert this block diagram to a signal flow graph. So I've already done this for you, but it could be a good idea to go through and try that yourself and just to verify that you get the same thing. So the next step then, if we're analyzing this with our Mason's rule, is we want to determine how many forward paths we have. So as usual, we have this sort of straight through forward path here, but we also have our forward path that dips down like that between V1 and V3. So just like with the last case, we have K equals 2 because we have two forward paths. So we have our two forward path gains. So of course the first one again is right along there, so that's going to be 1 times s squared, and so I've left off a gain for this one, which is 1 over s. So for our T1, our first forward path gain, we're going to have 1 times s squared times 1 over s. And so of course this is a little different because now we're not just dealing with sort of vague arbitrary g blocks, we have actual values for these systems. So if we multiply that out, of course we'll just get s. For our second forward path, we have 1 over s, 1 over s. So our T2 is 1 times 1 over s times 1 over s, which is of course just 1 over s squared. So the next thing that we want to do, working towards finding our delta, is to identify any loops and the loop gains. So in this case, we actually have 4 loops. So we have one loop here, one loop here, one loop here, and finally one loop here. So again, remember our definition of a loop, we're starting and ending at the same point and not going through any node more than once. We notice that all of these loops share node V1, so they're all going to be non-touching loops. Or sorry, rather they're all touching loops, we have 0 non-touching loops. So let's first write our 4 loop gains. So 4 loops, so our loop gain 1, we can say is equal to, and so for 1, let's say that was this path here, so we have s squared times negative 1. So s squared times negative 1, which is of course just negative s squared. Our L2, let's say, is that other sort of simple loop. We have 1 over s times negative 1, which again is just pretty obvious. But let me write it out for clarity. So we have 1 over s times our negative 1 is just negative 1 over s. And then we have our sort of slightly longer loop. So s squared times 1 over s times negative s. So that's going to be our L3. So we have s squared times 1 over s times negative s. And so the s and 1 over s cancel out, so we'll be left with a negative s squared. And then finally our L4, so coming back up here, we can see for our L4 we're going to have 1 over s, 1 over s, negative s. So we have 1 over s, 1 over s, and negative s, which will give us a negative 1 over s. Again, we have 0 non-touching loops. So all of our loops share that node V1. All right, so we're now ready to write our delta equation. And so because we have 0 non-touching loops, that makes our equation for delta a little bit simpler. It's just going to be 1 minus the sum of our loop gains. So 1 minus the sum of those 4 items, L1 through L4. So what that ends up being is we have 1 minus, and we notice that we have sort of 2 of the similar form. So we have 2 s squared terms and 2 1 over s terms. So just sort of combining those, we get a negative 2s squared minus 2 over s. And from there, we're going to do some algebra to sort of simplify this further. So in that parentheses, we can, of course, factor out a negative 1. Combining terms by finding the common denominator of s, we get 2s cubed plus 2 over s. And then if we want to combine that 1 out front in as well, we get 2s cubed plus s plus 2 over s. All right, so there is our delta term. So now we need to figure out what our delta 1 and our delta 2 are. So for our delta 1, we want to consider our first forward path t1. So our first forward path t1, we notice that t1 touches all 4 of those loops. And what we're going to see is that the same is true for our forward path t2. So because both forward path touch all 4 loops, we're going to have both of our delta terms equal to 1. So let me go ahead and adjust this and say, let's just say both forward paths. So both forward paths touch all 4 loops. And so you could try to do that alternate method as well for some practice, where you redraw the figure and physically remove our forward path. Any loops that are broken or open, you substitute a 0 for their loop gain in the delta equation. But in this case, because our forward paths touch all 4 of our loops, we just have delta 1 equals 1 and delta 2 equals 1 as well. So at this point, we're ready to plug into our general formula. So we have that our overall transfer function g of s, and I'm going to write it a little bit differently. So I'm going to put our 1 over delta out front. The only reason for that is because we already have this form here, and we can see that that's going to look a little nicer if we're able to invert that before combining it with stuff. So then that's multiplied by t1 times delta 1 plus t2 times delta 2. Now, of course, our delta 1 and delta 2 are just 1, so that becomes a little easier. So we have gs is equal to, inverting our delta function from before, we have s now in the numerator, divided by 2s cubed plus s plus 2. And now, again, because delta 1, delta 2 are 1, we essentially just have t1 plus t2. And so just as a refresher, let's scroll up. So our t1 was s, and our t2 is 1 over s squared. So we have s plus 1 over s squared. And so let's go ahead and sort of combine those two terms. So just copying our 1 over delta. So we have s over 2s cubed plus s plus 2. And combining those two terms, we have s cubed plus 1 over s squared. So now, of course, we can cancel out this s with one of our s's in the denominator here. And we get that our g of s is equal to, so in the numerator, we have the s cubed plus 1 still. In the denominator, we multiply that s term through to get 2s to the 4th plus s squared plus 2s, which, of course, as we would expect, is the same result that we got from doing our block diagram algebra. And so that just illustrates how you can do either one of these methods. Of course, if we're given a system in one form, a block diagram or signal flow, it might be easier to stay in that form. However, you do have the option to switch to the other form and use the opposite method as well. If you would like some more practice with Mason's rule, you can look at example 5.7, which is on page 252 in the 7th edition. So sorry, at the moment I don't have the updated page number. Forgot to check before making this video, but it should be around that page number in the 8th edition.